it's a privilege for me to introduce Professor Enrique Zuazua, who is no stranger to Chinese mathematicians, because maybe this is the only summer he couldn't come to China. He used to spend a lot of time.
That's true.
Briefly in Shanghai, but mostly in Chengdu.
Yeah, that's very unfortunate that I cannot go there.
He's certainly very well-known applied mathematicians. Was a member of this Academy of Europa, and also invite speaker at ICM 2006. And moreover, he's also an ambassador of mathematics to the society. So he constantly speaks to government officials, maybe even the king, the media, the public about mathematics. So it's really great pleasure that Enrique accept our invitation to give this speech. So now the floor is yours, Enrique. Please, you can start. Can you share your screen?
Yeah, so let me see. Okay, here it goes. Let's go. Do you see my screen?
Yes, perfect.
Okay, so thank you, Xi, for this kind invitation, and thank you for all of you to be with us. For some of us, it's the evening, Friday evening. For some others, it's Friday morning. And I got a friend yesterday that was sending me an email from Brazil saying, well, I'm not sure I will be able to attend it because it's 5 a.m. in Brazil. So we have at least 3 different time frames. Good. So for me, it's a privilege to have the opportunity to be with you today. The institute that she is running in Shanghai has been always doing very well, and now of course they jump very quickly into this Zoom world, and as she was saying, is a great tool, right, that allows us to be all together in some weak sense, right, although we will not be able to share a tea or a beer afterwards, right? Good. So let me then get into the topic. So these are reaction diffusion models. This is just one modeling that you could adopt for the topics I am going to present. And we are addressing them from the perspective of control and dynamics and also numerical simulations, problems motivated mainly in social sciences and biological sciences, but of course, we address them from a mathematical perspective. I don't claim that any of the results here are accurate enough to be, say, usable in practical applications so far in a precise quantitative manner. This is a joint work for a number of years with several junior fellows like Idriss Mazari in Paris 6, Dario Piguin in Autonoma, Camille Pujol also in Paris, Domenech Ruiz in Autonoma as well, Emmanuel Trela, who is a professor in Sorbonne in Paris 6, and Yamin Zhu, that was also a postdoc with us in Paris 6. The general motivation, as you can guess, is that, I mean, this is a message that for this community is not really very necessary, but this is still always important to stress, is that from an applied math perspective, if you want really to develop a full, say, plan, you have to address modeling issues, analysis, simulations. We all know all this. But then often in practical applications, there are also topics and problems related with design, optimization, parameter identification, control that can appear in a way or another. And as you know, the boundaries of these fields are not always completely neat, right? So it might very often depend on the kind of modeling you adopt and how you formulate the problem, that it might look more like a control problem or rather a parameter identification or an inverse problem, for instance. So you can find in our ERC grant DICON, we have developed an intensive, say, research agenda, and we have also added a number of contents in our DICON blog where our researchers have described in a more or less friendly, dissemination-oriented manner the kind of topics and tools we have developed. Okay, so the motivation of this talk came from a conversation with my friend Jose Ramon Uriarte. He's a senior professor in economics in Basque Country, and he's a game theorist. and he was interested on the modeling of minority languages, right? So as you know, in Basque Country, everyone speaks Spanish in the Spanish side or French in the French side, and there is a minority of people that really master Basque, the minority language, sufficiently. But it has been always observed in all the statistics that the use of the language, in principle, seems to me much below its potential, right? And the conclusion of their study, they developed a game theoretical model, was that there is some kind of politeness equilibrium, right? So politeness equilibrium means that when you are, I see Varga, for instance, here, right? So he's from Azerbaijan and he's traveling and then he meets another person. And then, so before you go to talk to this person in the minority language, otherwise, of course, if you are in an airport, you will address this person in English, you will observe whether this other person exhibits signs that is able to speak the minority language, right? And there are signs that are weak, right? So for instance, if you see someone with a t-shirt of Messi of the Barcelona soccer team, this doesn't mean for you that this person speaks Catalan, right? So there are like a few million people speaking Catalan. There are hundreds of millions of supporters of Messi around the world. So inconsciently, there is a game that you develop within your brain very fast, so to detect signs, to be able to determine whether this person is able or not to speak, say, your minority language. Of course, this can also apply to majority languages like Chinese. When you are traveling in Asia, I suppose that many of you, when you are in a different airport outside the country, you will find a person, and then before addressing this person in Chinese, you will look for signs that this person is really able to speak in this other language and not the natural language, the majority language within the airport you are, right? So, and then of course, whenever you see that this person is reading a newspaper in that language, then this will be probably a sufficient sign for you to switch to this language. But then when you are in the street, right? I mean, it will not be easy for you to determine from the external signs whether this person is able or not to speak this minority language, and therefore not to generate any uncomfortable or unpleasant situation, you will have the tendency to go to the majority language, which is more comfortable for everyone, and this is the politeness equilibrium. And this is one of the reasons that explains why people, right, tend to use their minority languages less than they could. Okay, good. So when he was telling me about this, I have seen that they were making a purely game theoretical approach and developing some ODE dynamics. And I thought, as a PDE person, that ODEs were kind of insufficient, right? Because in particular, you don't take into account a space distribution. And we know that, of course, in this minority language game, you know, things can dramatically change from one region to another, from one valley to another, right? So a space distribution seems to be extremely important. And then browsing the literature on this topic, I have seen, and talking to different experts, one of them will tell you, well, you should use kinetic modeling because people are like particles in Boltzmann. When they meet together is like when particles collide, and then there is an interaction, and there should be a kernel taking into account, you know, the goal and the level of mastery of the different languages of every individual. Yes, you could go to, some others will tell you, well, definitely you should work on networks, because when you look to nowadays to the communication network of a country, what you see is a space distribution which is governed by a network along which communication is being driven, and so on, right? So what I adopted the more classical model of that you certainly know from many other, say, previous experiences. Maybe Kolmogorov was one of the very first ones to introduce this model, which is the bistable reaction-diffusion problem, right? So in this model, the world is governed. We assume that we are in a flat world, one-dimensional. Of course, my analysis can also be developed in multi-D as well. Many of the techniques can be adapted to multi-D with, of course, more limitations than in 1D. But let us assume that we take the diffusion operator, which is diffusion, the tendency, the behavior of people, right? And then there is a nonlinearity, which is bistable. There are three, say, equilibrium trivial configurations, 0, theta, 1, and the nonlinearity, which is drawn here, right, simply indicates, well, when you are below theta, you have the tendency to go to 0. When you are above theta, you have the tendency to go to 1. So this will be in our context of minority languages that, well, if you are poor on language in question, you will have the tendency not to use it. If you are very fluent, you will have the tendency to, you know, to use it further. For instance, talking about COVID, where we have seen that the impact on people depends very much on age. Theta could be an age parameter in which it says, well, if you are below a given age, the probability that this sickness becomes severe is low, while when you are above a given age, you have to really pay attention because, the infection can be much more severe, okay? So then eventually we are led with a density function y, which is describing at every x and every t, the volume fraction of people on a given category. And y indicates how do you stand with respect to this scale 0, 1, in which the critical value is theta, because it's the one that determines whether you have the tendency to go down or go up, okay? This is a generic model that has been introduced in many different contexts, neurosciences, genetics, waves in chemical reactions, and so on. So the parameter A is a positive parameter. You can think on it as being A equal 1. It's just a scaling parameter, and the only thing that it does is to accelerate the process, right? Depending on whether A is larger or smaller. And then theta, this critical parameter, is called the Ali threshold, okay? So the Ali threshold, as I have said, has the impact that for y smaller than theta, there is a negative population growth. This population has the tendency to go to 0, while for y greater than theta, it has the tendency to saturate, expand, and go to the value 1, right? And then in practical applications, of course, in particular in biology, the value of theta is a control parameter, right? For instance, you can use vaccines in order to try to push this threshold theta of people that are in need or are in safe side, to a larger value, so to cover large percentages of populations. In some other biological, say, applications, you can, for instance, use the sterile male technique in order to, say, kill, populations of invading insects, okay? And then in this model, as we have already seen, by now I am considering the Cauchy problem, no boundary conditions, no domain, just the real line, the Cauchy problem. There are obviously three distinguished solutions, which are constant, 0, theta, and 1, right? But there are other very important non-trivial solutions, which are the so-called traveling wave solutions. So what are traveling wave solutions? Traveling wave solutions are solutions U that propagate in space, right, with a given fixed capital U, taking values 0 at 1, the two stable equilibria for the ordinary differential equation underneath, right, when you drop diffusion, right, taking 0, 1. Of course, you can swap the drawing because the equation is symmetric, right? But what is tricky in these traveling wave solutions is that in principle, there was no reason. When you look to the equation, you see this is something purely symmetric. There is no convective term. There is no transport. Why waves start moving, right? Actually, the velocity of propagation c for these traveling waves is something that you can relate to the profile of the solution and actually of the nonlinearity. You see in this formula, as I have written there, that the sine of c is equal to minus the integral of f, right? So then depending on whether f is more positive than negative or the reverse, right? This will determine the sign of f, and this will also determine the sign of propagation of c. So you see in this drawing that, when c is negative, the traveling wave is traveling to the left, and then eventually, if you look to the asymptotic behavior of this reaction diffusion problem, locally in compact sets, you will see 1, right? Because, you know, when C is negative, the wave travels to the left, and then even if you are originally 0, the one wave, the tsunami, will come from your right and eventually will cover the domain by 1, right? By the contrary, when C is positive, the traveling wave travels to the left, and then eventually it will be the 0 population that will occupy the domain, right? So it's either waves moving forward or backward. In this very particular case, where the nonlinearity is the cubic one I gave you, the profile of the traveling wave is explicit, and by this exponential transition formula here below. This one was maybe computed by Kolmogorov for the first time or so. And it's interesting that in this case, the explicit form of the shape of the traveling wave is independent of the parameter theta, right? The only thing that the parameter theta does is to regulate the speed of propagation of the wave, right? So in the formula below, you see how when theta, for instance, is equal to 1/2, you are in the purely symmetric case, right? Where the nonlinearity is symmetric with respect to 1/2, then the velocity of propagation is 0. This means that the traveling wave becomes a steady state solution. While when theta grows or diminishes, then you start generating either a positive velocity or a negative velocity. And the critical cases are when you reach the extremal values, theta equals 0 or theta equal 1, in which the absolute value of the velocity then becomes the square root of a/2, right? So it means also, and this is important from a control theoretical perspective, that regulating the theta parameter, you can also accelerate the effect of traveling wave, the velocity of propagation of waves. Okay, good. So I'm trying to, sorry for this. Okay, so traveling waves, you know, you have them in the stadium, for instance, in the sport or soccer stadiums. You see that a traveling wave is la ola, we call it in Spain, is the wave. You are standing in the stadium. I mean, you went there to be sitting and watch the match, and then there are the fans of one of the teams that they start waving. You know, one is lift. And then, you know, because the other one is doing that, the next one is doing the same, the next one is doing the same. So you see that while you are standing, you are pushed somehow to join this traveling wave and to switch from 0 to 1, right? So this is an spontaneous emergence of some motion that is hidden underneath. So when I try to explain this to younger fellows that are not familiar with traveling waves, but they are more, say, in the computational aspects of PDEs, I try to explain this phenomena by the classical idea of splitting, right? Domain decomposition splitting, as you know, is one of the fundamental, say, tools in scientific computing for partial differential equations, right? So we can always say that this reaction diffusion problem, now I have taken to simplify the parameter A to be 1, right? This reaction diffusion problem can be simply seen as the superposition of the ODE. I drop the diffusion and the diffusion. And then you say, well, but these two models are very simple, right? These are in the book, right? Because the diffusion is very simple. I just applying the Gauss convolution kernel. And the ODE, well, the ODE is also very simple. This is just a simple cubic ODE. I can solve. I can analyze the asymptotic behavior of solutions. And I know that the solutions that are below theta, they will go to 0. And the solutions that are above theta, they will go to 1. What happens then? So think in the beginning that you have an initial datum, which is a Heaviside function, 1 and 0. What happens then? When you apply the ODE, this Heaviside function is cut asymptotically at the level theta. And then all those that are above 1, above theta, will have the tendency to go above. And all those that are below theta will have the tendency to go below, right? On the other hand, the diffusion will simply regularize symmetrically And when you say combine these two phenomena, you will indeed see that there is motion that emerges. So this is done in this simulation where I start by this, say, initial datum, right, which is this red line. Then I do this iterative resolution of the ODE plus the diffusion operator, and then you see how, you know, the wave starts traveling. So here you see these oscillations. This is done in purpose because here in the splitting algorithm, we have taken delta t, the splitting step, not to be too small, so that you really see this impact of splitting. But of course, if you will diminish delta t, right, then you will see a much closer, smooth evolution with respect to the one that, you know, the full nonlinear diffusion dynamics represents. So this is a fundamental aspect in the theory of traveling wave solutions. Both models are purely symmetric with respect to X, apparently, but the lack of symmetry of the nonlinear ODE with respect to the values of Y eventually leads to this important traveling wave phenomena. And this is why, you know, in social behavior, there are so many ways, right? You know, not only for dressing, but also for political opinions. And in this case, we could say that we have been driven by the Zoom wave, right? That suddenly has invaded our world of scientific communication. Okay, so now if you want to control these systems, you know, controlling a system is like when you try a toy for the first time. I mean, you can read the book of instructions. This is something very boring, or you can start playing with it. And when you start playing with it, you have to learn what are the main features, how the solutions respond to some of the parameters. And basically the theory for traveling wave solutions and the asymptotic behavior of reaction diffusion problems was developed 45 years ago. There are many articles on this, but certainly these two, the seminal papers by Aronson, Weinberger, and are worth to quote, right? So what do you see then when you simply understand how waves behave and then you try to simulate that, for instance, in MATLAB? This is what you see. So in this, on the left, you see an initial datum, which is a very minority population of ones in a world surrounded by zeros. This is a very narrow minority in a country surrounded by zeros, a minority of ones in a world of zeros. But there is some enhancement of this minority, right? If the parameter theta is very small, so that this minority has good conditions of development, then you will see the dynamics on the right. You will see that this narrow red column starts growing and then diffusing and then propagating to the left and to the right. And what you see here is front on the right and a front on the left. You see how the solution evolves into two superposed traveling waves that are growing and growing. Of course, this process will continue endless until locally in compact domains, as t goes to infinity, the solution will go to 1. By the contrary, the same population in the same world, if the policy is very tight for, you know, this population to reproduce and to evolve, this means taking the theta parameter larger than 1/2, for instance, 0.7, then this population will have the tendency to extinguish, right? And this is what you see. You see how out of this red, say, column, you see how by diffusion, the solution is being attracted exponentially towards 0, okay? Then how do you represent that by the existing theory? This is one, for instance, of the theorems. This is summarized here in a very brief manner, but you can find this kind of results in the articles I mentioned before. The theory says the following: the Cauchy problem, this equation, and take an initial datum y0 general, and assume you have two asymptotas, one to the left and one to the right, right? And assume that these two asymptotas are separated by some theta, right? Some critical level theta, right? And that this theta is precisely the Ali threshold of your nonlinear equation. Then what the theorem says, this solution will eventually behave as t goes to infinity as the traveling wave solution. Of course, there is an important ambiguity in this kind of results. is that is due to the fact that traveling wave solutions are translation invariant, right? So you see that in this exponential convergence formula down there, right? I'm saying that y converges exponentially to u x minus ct. This is the traveling wave, but translated to x1, right? So the center of gravity of the traveling wave somehow depends non-linearly and in a subtle manner on the initial data, right? So the asymptotic values of the initial datum below and above theta are able to determine the convergence to the traveling wave. But in order to get what is really the center of gravity of the center of the traveling wave, you will need more information on the initial data. Now, with this, this is our first result on this topic in a first paper with Jiamin Zhu and Emmanuel Trela. I think it was published in M3AS. Right? We said, well, we could use these to control solutions, right? So this is the kind of theorems we prove. Assume now you give me a general initial data, y0. And the only thing I assume is that the asymptotic limits at minus infinity and plus infinity are different. Now, as soon as they are different, I can always place, right? Now I am making control. So now I am the one that determines what is the Ali threshold, right? I am allowed to regulate the value of theta. Now, what I do is I choose the Ali parameter theta, right? Which is right in between, somewhere in the interval described by these two asymptotes. Now, I keep this control fixed, right? And because of the previous asymptotic stability result, I know that the solution will converge to a traveling wave. So eventually, after some time, you will be very close to the traveling wave. But maybe the traveling wave will be very far, right? And then you will like to bring back the traveling wave towards the area in which you are really interested in the dynamics of the system. How can you produce this shift of the traveling wave? Well, once you are close to the traveling wave, you can switch from this initial value of theta to a different value of theta, right? And then in this way, as I have mentioned before, you can regulate the speed of propagation of the traveling wave towards the left or towards the right. And then eventually you will know that you reach not only the traveling wave, but that the traveling wave stands where you wish, right? So this is a very good example of how a good understanding of the dynamics of the system, plus this very simple idea of bang-bang control, choose first a theta parameter and then switch to another theta parameter, well chosen, both with respect to the length of the time intervals and the actual value of the parameter, then you can control the dynamics towards the traveling wave. You could do that also numerically, and you will expect originally to say, well, if the theory says so, it should be very easy to see computationally. How you formulate that computationally? You could say, well, in my PDE, I will assume that theta is a control parameter depending on t, and I will ask the computer to optimize, right? So to minimize the distance of the solution at the final time towards the profile of the traveling wave, one that I choose a priori. And then the computer should be able to find the value of this time-dependent Ali threshold theta t. How you do that? Well, you discretize and then you use the software you like in order to minimize a function. After all, this is just a function theta depending only on t. I mean, from a control theoretical point of view, I have given you an example. You have other examples, for instance, in this paper by Canarsa and collaborators about the bilinear control of nonlinear diffusion. This is a big topic. Kapalov has written many articles on this. This one was also in collaboration with Giuseppe Floridia. There is also a literature about Schrödinger in the context of laser design of molecular systems. So bilinear control of nonlinear PDEs is a topic in itself. Now, what I wanted to emphasize here is that finding the strategy I have mentioned to you, which comes very naturally from an analysis perspective, finding that a strategy computationally is not so easy. Why? Well, because the dimension of the system grows significantly. So actually, in order to be able to solve efficiently this kind of control problems or design problems, it is always better to use a two-grid strategy, right? So we have explained this in a paper published in 2011 with Casado Diaz and co-workers in the Science Journal of Multiscale, right? Where we say there we are looking to the classical problems of optimal design of coefficients for, say, composite materials in elasticity, right? Where there is such a big, say, literature from the perspective of homogenization as well. And we emphasize the following thing. And this is something that, you know, is one of the key messages, right? When you are doing numerics for control, you need to use a multi-grid approach. This was already indicated in the pioneering works by Glowinski, Lyons in the 80s, and so on, right? You need to use a two-grid approach. Why? First, you need a very fine grid in order to discretize and approximate the dynamics you are considering well. So you need a fine grid for approximating the PDE. But if you use the same fine grid in order to approximate the control, then the control has too many degrees of freedom, and very often this leads to poor performance of optimization algorithms, in which, you know, the computational burden becomes unfeasible. So here, maybe we could try to apply the ideas recently developed by Shijin and collaborators on the random batch methods, which are somehow inspired on the Monte Carlo, say, methodology, right? But if you proceed in a classical deterministic way, the algorithm will not work well if you use the same fine grid for the control. But on the other hand, you say, but the control is very simple. It's just two constants, one constant first and another constant after. Why do I need a control that is so complex, taking different values for every time step delta t, if eventually there are only two key values in the control parameter, right? And this is why, in order to capture this simpler dynamics of the control, and in order to reduce the computational burden and make the algorithm more performant, you better take a coarser grid for the control, okay? And of course, the game to play is what is the critical, say, ratio between the fine mesh and the coarse mesh so that your algorithm works optimally, right? And this, of course, is something that depends on the problem. All of this is about somehow eliminating the spurious effect of the unwanted high frequency numerical oscillations. Okay, so the summary of this first part is, well, you can use these models, you can understand, learn from, you know, our understanding on the dynamic behavior and implement a number of control strategies. You can even develop numerical algorithms that are able to, you know, to find this kind of optimal control strategies. But, and you can do that just by regulating the Ali threshold, but the impact is mild in the sense that we had to make an effort in order to just get to the traveling wave profile. And you see, because we rely on some exponential stability results, the time you will need to do that is long, right? In practical applications, it's very natural also to consider the same problem now when theta is fixed, but with boundary control, right? So now I go to the second part and I say, well, maybe practical applications is better to think in, you know, in your region, in your country, in your town, your neighborhood, where, you know, the space domain is bounded, right? The Ali threshold is fixed because the way people behave doesn't change from one day to another. There is a, you know, a social behavior that is common to everyone and is well established, right? So theta is fixed, but there is people coming and going out. So you can, in some sense, regulate, you know, the flow through the boundary. You can regulate, for instance, immigration, how many tourists you allow, right, to come in, or how many people you allow to go out, right, knowing that the epidemics is still evolving. So then in that case, the problem becomes, can I use controls U and V, which are in between 0 and 1? Can we find controls U and V, which are in between 0 and 1, so that we can regulate the dynamics of this nonlinear PD now in a bounded domain? What will be natural goals? So in this paper, in collaboration with Camille Pujol and Emmanuel Trela, published in Nonlinearity, what we did was to take as goal, well, the simplest one. Let us just think on the constant steady states as goal, right? So the question is, given an initial datum, can I regulate, you know, the flow of population through the boundary in both of them, so that eventually in the final time, the solution reaches the constant equilibrium, the constant either the 0 or 1, which are the stable ones, or the theta, which is the unstable one from an ODE perspective. Okay, so in the beginning, we started playing, you know, computationally, and we said, okay, let us see whether I can drive the dynamics to 0. Okay, so this is the simplest goal, drive the dynamics to 0. So we have taken here an example where the theta parameter is 1/3, the initial datum is nearly 1, is 0.9, the length of the interval is 7, right? So the domain and the PDE are fixed, the initial data are fixed. So if I want to go to 0, I take 0 boundary conditions. This is the easiest, right? If you want to go to 0, you just put 0 on the boundary and hope that, you know, the population will freeze and cool down to 0. And this is what actually we see in the left picture. You see how out of the constant 1, you know, on the top left, we go to this kind of parabolic behavior. Then you see the dissipativity, and you see how exponentially the solution goes down to 0. So success, trivial result. Then we did it for L11, a longer domain. So you are now in a longer domain, the same initial data, the same nonlinearity. You do the same in the bigger domain, and then you see that the solution starts going down, but it doesn't go to 0. And you say, well, why is not going to 0? It's going to kind of some sinusoidal or parabolic function that is taking, of course, the 0 boundary values. It looks like a steady state solution that the dynamics have reached. Why is that? Well, in fact, when you look to the classical works, there were pioneering works by Matano, for instance, in '78 about the asymptotic behavior of nonlinear reaction-diffusion equations in 1D. And they will tell you, well, every bounded solution converges to a steady state. And then you say, well, but if this result is true, why this solution is not going to 0? I am posing 0 on the boundary. 0 is a steady state. Why it doesn't go to 0? Well, the reason is that depending on how large the domain is, there might be other non-trivial solutions which are steady states, right? And this brings us back to the classical theory of nonlinear say elliptic equation that was so much developed in the 70s, in the 80s, and still nowadays, right? Ambosetti, Rabinovich, and Palais-Mail, and all this, right? There is a nice survey article by Pierre in '82. But I mean, in order to understand what is going on, you just really need the very basics. And you say, well, we are talking about the steady states. So these are critical values in H10 of 0L of this functional, which is the mix of quadratic plus the nonlinearity. Capital F is the primitive of a small f. A small f being bounded, capital F has a linear growth, right? And now you want to minimize this functional, and you say, well, minimizing this functional is very easy because it's not convex, but it's convex plus compact, so it's weakly lower semi-continuous. It's coercive because the quadratic term dominates the linear one. In H10, 0L, this is a very nice Hilbert space, so the minimizer exists. Yes, but is the minimizer 0 or not? Well, it depends. You see what happens? When the domain omega L is very small, then the Poincaré constant, right, the eigenvalue of the Laplacian, which is pi squared divided by L squared, when L is small, the eigenvalue of the Dirichlet Laplacian is very large. This means a very large Poincaré constant. So it means that the coercivity of the quadratic term is huge. And because the coercivity of the quadratic term is huge, it absorbs completely the nonlinearity. And therefore, the minimizer is 0. And this is the case when L is small. And this corresponds to what we have seen. When L is even, you go to 0. But when L is large, right, the first eigenvalue pi squared over L squared is very small. And because it's very small, the coercivity of this quadratic term weakens. And the interaction with this nonlinearity may produce that there are winning, say, functions y in which the nonlinear term is above the quadratic one, and therefore the minimizer is below 0. So it means that when L is large, the global minimizer is below, and therefore you have a non-trivial solution. Therefore, of course, the result by Matano was true, but it says what it says. It says that in both cases, solution go to a steady state, but nobody says that the steady state has to be the 0 one. Is one of the steady states corresponding to the 0 values. In the small domain case, 0 is the unique one. In the large domain case, there are another one, and this can be the attractor. So the conclusion is that when you are doing control of these systems, even in the simplest cases, the structure of the landscape of the space of a steady state matters a lot. And actually, when you start analyzing the landscape of a steady state, you find there are very many. Of course, you know, this is for L large. This drawing was done by Dominic Ruiz. So when the domain omega is large, here I have just rescaled the domain to 1, but this is corresponds to a domain L, which is of the order of 15 or so, large. So you see, you have the constant trivial solutions, 0, theta, and 1, but you have other non-trivial solutions. For example, you see 2 red solutions, one above and one below, emanating from theta. This means that even if you take value theta on the boundary, other than the trivial theta solution, you will find one above red and one below red, right? Then when you look to 0 boundary conditions, other than the 0 solution, you see also 2 blue other solutions, which are non-trivial steady state solution. One is the global minimizer, and the other one is a saddle point, a la Palais-May, say. And you see also a green function here, which is, I mean, it's a green solution, not a green function, it's a green solution, which is taking values which are very small, but not 0 on the boundary. And this corresponds to an standing wave, which is a steady state solution of the problem in the full space, taking values at infinity. So when you chop off in the domain 0L, you see these small traces. So all these functions, you know, are steady states, and they are candidates to attract your dynamics. And of course, this can be an impediment for you to go to 0, because in particular, the maximum principle, right? And with this drawing, you understand what's going on, right? So if you start with an initial datum, which is below the smallest blue line, then you will go to 0. But if you start above one of the blue lines, if you impose 0 boundary conditions, you will always be trapped above these steady states. And this is what happens when the domain is L is large. So last summer we were discussing these topics in a summer school in Chengdu, and Dominic found this interesting article where the application is exactly, you know, goes in this direction. And the claim in that article is, well, you know, Chengdu has the highest population of pandas in the world, right? And but there they explain, you know, the pandas, I mean, you cannot grow pandas in your apartment or in your garden, right? So pandas need a large forest, right? So you need a large area for this small population to grow, right? And this is precisely what we are saying here. As soon as the domain is large, there is the possibility of having, say, populations that self-organize in a non-trivial manner, right? So pandas can live in large parks. They could not live in small parks because for L small, the unique steady state is actually equal to 0, right? Taking into account that 0 is the boundary conditions out of this park where this is mainly populated by people and very urbanized, and this is an hostile environment for the pandas to grow, right? Okay, so now we have seen that when you take 0, you go to 0 in some cases. In this particular case where theta is 1/3, 1 is favorized. So if you take 1 boundary condition, you will always go to 1. And we said, well, what happens to the steady state theta, which is just in between? Can I drive the population to this politeness equilibrium, this compromise theta, which is unstable from an ODE perspective, but that after all is a steady state for the diffusion problem? And then we said, well, in principle you can, right? Because in fact for theta is easier because we try to be in between 0 and 1, but theta is in between, so you have room for oscillation. So you can immediately apply some of the existing local control results for parabolic problems. They are technically, I mean, quite complicated because you have to use Karleman estimates in particular, as developed by Fursikov and Manilov and collaborators afterwards, right? Also Lebor, Roviano, many deep results in the context of Karleman inequalities for parabolic problems. But definitely you can apply that theory, and then you will have a local result. The local result will be, if you are close to theta originally, then you can go to by regulating on the boundary. Yes, but we wanted global results. What happens if I just are given an arbitrary initial datum? Well, if you are given an arbitrary initial datum, then you can play the same strategy as before. Fix theta on the boundary. Because of Matano, you know that the solution will go to a steady state. When you get close to this steady state, you apply the local control result. Yes, but the problem is, as we have mentioned before, is that there might be barriers like this. Oh, but then if there are barriers, maybe if I put theta, on the boundary, I will not get to theta. I will get to one of the red solution up or down, and then I will be still very far from theta. How can I manage that? Well, when the domain L is small enough, again, there is a unique steady state, and this strategy works, but when the domain is longer, you cannot do that anymore. So in order to overcome this and try to understand better what are the real limitations to go to theta, then we realize the following thing. Okay, so when you want to go theta, you still can take boundary values that are much below. So maybe we should first freeze, right, the dynamics, taking 0 boundary values, so that the solution is allowed to go below the possible red barrier. And once you are below, start activating the control strategy, right? So this is like in many processes, right? You don't act immediately. You expect, the crowd to get to you before talking to the crowd, right? So you don't start screaming when they are too far. You just say, okay, it will take me some time, but these people are coming to me. And once they are close to me, I will ask them. So assume you are driving in Shanghai, you are lost. And then, rather than screaming from your car, well, you wait until some citizen walks close to you to then kindly ask, can you please advise me about, the address? So there are many processes in real life in which the control is possible, but cannot and should not be implemented very rapidly. But rather, you have to wait until the dynamics comes to you in a more favorable, say, configuration for you to control. And this is what we did. Using this idea, that I will go back to it, is that oftentimes optimal control strategies are not brute force and require some smart, say, combination of different actions in order to succeed. And this is actually the idea behind the Kalman brackets and Lie brackets and so on in the context of linear and nonlinear control, in order to enjoy of the wealth of the dynamics in order to be able to manipulate trajectories, right? And then the final sharp result that was proved in this article with Pujol and Trelat uses a classical idea that was already presented in an earlier work by Corona and Trelat, which is build bridges of steady states, right? So you can directly try to control the parabolic dynamics, but it is much easier to do it if you first build a bridge of steady states and then you walk along it. This is like when you open, the Google Maps, right, in order to see what is the path going from the origin to destination. And when you have this global picture of the road, then you walk or you drive along it, probably small deviations and oscillations, but allowing you to go from origin to destination. And in this result, then you see that the strategy is more complex. It's not going straight to theta, but rather first cool the system down to 0 to hit up, right? And this can be done in a say optimal manner in 1D, in particular because in 1D steady state solutions are a second order ODE, and then you can have a complete understanding of the space of steady states, which is of course not simple. So here in this drawing, you see the classical phase plane description, W in the horizontal axis, W prime in the vertical axis. You see this blue, say, kind of peaky ellipsoid or almond, right? So this blue line is the steady state solution in the full space, which is taking zero boundary values at infinity, right? So this is the ground state in the full space. You have the zero solution, you have the theta solution, which is in the center of the almond. You have also the one steady state solution. And then the important thing is that the dynamics within this blue almond here is totally stable. And then you can, modify the trajectories within, right? Trying to, by regulating the parameters, the boundary values, trying to link the different, say, steady states. And this is what we did. Once you understand that, you do a little bit of sorcery, and then you understand how in the optimal range of lengths, right? You can, for instance, on the right, you see how you can go from the green zero trivial solution to the blue dotted theta solution by an arc of solutions, which is non-trivial, because in particular, for some values, they are going above theta, but eventually, the family, the one parameter family of a steady state solution joins 0 to theta, right? And this can be done by simply using the trajectories of the ODE within this amount. This can be done, as I said, only for L small enough. Why? Because when L is too long, then you see this dotted black line, right? Which is also a steady state solution, right? That cannot be joined, cannot be modified from the original ones by, say, diffeomorphic deformations, right? So this result is sharp, yet is only true for L small enough, right? Because for L large, there can be, say, lack of control properties. And the same remarks, but now developed from a, say, better perspective, you can even see that there are families of even steady states that are able to join 0 to theta. This is an interesting result because in our first paper with Domenech and with Pujol and Trela, our theory required controls that were different on the left and on the right, but the numerical simulations really exhibited controls that seemed to be even. And it was the remark by Domenech, is that you simply symmetrize the way of understanding the phase plane, and then you can find also even solutions. Okay, so just to get to the conclusions, you see, after all this, what are the, the kind of basic principles? Well, the basic principle is you like to combine the stability properties of the system. You can do that. The stability properties of the system can be tricky because sometimes you go to steady states that were not those that you were expecting to reach. But you can also analyze the landscape of a space of steady states, right? And once you find bridges from one steady state to another, then you find more elaborated ways of controlling the dynamics. And in this particular case, we did it first down to 0 to then go up again. So these are like these hotels in which there are like two buildings. You are sitting in one building, your colleagues are sitting in the other one. And then when you want to visit them, you cannot go from your room but to the other room, but you have to first take an elevator down to then go to the other building and take the elevator up again, right? This is what we were doing. But we were curious. We said, well, this was our analytical method. Maybe there are better bridges to do this. And therefore, we ran a numerical simulation. And for our surprise, it was very nice to see how, as you see in the figure in the left down, you see that the optimal dynamics is precisely what it does, right? This was found using the optimization software IPOP, right? And you see how the algorithm, in order to link this initial value, which is 0.9 to the value theta in the limit, then it has first to go down to then go up again. So analysis allows to sometimes at least guess optimal paths, and then numerical simulation is able to confirm and of course provide a more precise understanding, in particular about the minimal time. All this requires substantial time interval. So the conclusion is that the optimal control strategies are not necessarily simple. I mean, you could think on it with a simple mind, but then you will not get very far. If you really want to enjoy the possibilities that the dynamics provides to control the system, then you have to really exploit its properties in a very fine manner. One way of doing that is, in particular, to try to exploit the landscape of the space of steady states. But this is tricky, in particular, because now you see the control is on the boundary. It will mean that you have to revisit the existing theory for solutions of elliptic problems with non-homogeneous boundary conditions, right? But if you are able to do that, then you can find unexpected bridges linking non-trivial, say, steady state solutions that they can be barriers for you to control, but they can also be your ally because they can be paths for you to get to destination in an unexpected manner. Of course, the similar analysis can be done in the radially symmetric case, right? And therefore, you know, embedding any domain by a fictitious domain technique, embedding any domain bigger disk and then restricting, you can find similar results as those I have presented here for the same reaction diffusion problems in any bounded domain of the Euclidean space. This was just a simple, model. Just to conclude, a comment on these GenFlow models that are very interesting. I mean, this was a suggestion made to me by Laurent de Villette and Raoul, right? That are experts in modeling of population dynamics. And they said, listen, Enrique, there are many models in which you rather that a GenFlow, say, perspective, right? What is the GenFlow perspective? This leads to basically a system of reaction diffusion equations. Because you say, in this perspective, you rather say, well, population is moving, right? People move from one place to another, you know, for jobs, for better houses, for better schools, for better climate, whatever. The people move. So there is a propagation of population. And the gene, in this case, will be the bilingualism, for instance, or the political opinion, or the religion, or any other genetic, say, or sociologic trait of this population moves with this, say, macroscopic physical motion of the population. So you have one reaction diffusion problem for the motion of the population, and underneath you have a second reaction diffusion problem, which is driven by this bigger motion, right? But that is, say, encoding and transporting the genetic trait you are interested on. When you do that, and in particular, you consider that the population is moving in a Gaussian manner, then you will find this kind of reaction diffusion problems with extra transport terms. And because of the presence of these transport terms, you can encounter, of course, like in this Fokker-Planck equation, you can encounter new phenomena, right? And one of the new phenomena we observed in this article with Idriss Mazari and Dominic Reed is that even though in the absence of this, say, population dynamics drift, right? In the absence of drift, one, the trivial constant steady state was always reachable. When you have this extra drift term, then there can be, you know, new non-trivial solutions taking boundary conditions equal to 1 on the boundary, but non-trivial, going down like this red parabola, which might become an impediment for you to reach this one steady state. So this is just to say that when you are getting into more sophisticated models in population dynamics, you have to get into systems. And when you get into systems, even if your original model was kind of reaction diffusion, you may have drift terms, and the drift terms can completely modify the landscape of a steady state, something that can become either, you know, a new source of obstacles, or rather also an ally. So just to conclude, some perspective. You can also, here I mentioned controlling the early threshold parameter or controlling the boundary. You can also regulate the diffusivity, right? And for instance, regulating the diffusivity, you can produce fingering phenomena, right? Why? Well, the reason is very simple. When you are here looking to these, say, steady state solutions that are twisting, turning around in the phase plane, when you increase the diffusivity, this is like increasing the size of the domain, and then this allows you to turn around a steady state several times, right? So if in a given domain you increase the diffusivity, right, or diminish the diffusivity, then you can see phenomena. In this case, it will be diminish the diffusivity. You can see steady state solutions which are, you know, oscillating a lot. And in this way, if you allow yourself to also regulate the diffusivity parameter, you can, of course, enrich the space of targets you can reach by, for instance, moving from a population which is more or less into homogeneous into a much more complex population in which you have these fingering phenomena, like in an homogenization process in which population of two different, say, characteristics are intertwined, right, in a more or less periodic and heterogeneous manner. So there is plenty of room also of further development controlling the diffusion. And then, of course, there is significant work to be done from a modeling perspective. I mean, to which extent all this can be done in a kinetic setting, and whether, you know, out of this kinetic setting, you can pass to the limit and recover this kind of control dynamics in a more or less regular manner, smooth with respect to the singular penalty parameters. And as I said before, probably the greatest challenge is to go beyond these nice ideas of analysis, numerics, and dynamic control to really be able to tackle, say, challenging real world problems in a way that you can be really quantitative and of, say, help to society. I mean, but as we all know, there is a huge gap between, say, mathematical modeling and real life complexity. Thank you for your attention. I hope it was not too long, but I'm sorry I didn't have a watch, so I could not really match maybe the time window. Thank you, Xi, again.
Well, thank you, Enrique, for talk. Well, before I open for the questions, I just want to make an announcement. Well, first, today we had like over 220 participants. So for later Friday afternoon talk, this is certainly phenomenal. Well, I'd like to make an announcement. Next week, we have two excellent French speakers, Silver Saferti on Tuesday and Francois Gauss on Friday. For those from Europe, I mean, Silver is from New York, so watch the time. Then in about 3 field medalist Alessio Figali will also speak at this lecture series. So just stay tuned and just check our website for future talks. All right, so now we are open for questions. Any questions from the audience for Enrique?
Hello.
George, how are you?
Yes. Hi.
Hombre, George, where are you?
Yes.
I see your hand.
Abu Dhabi. Abu Dhabi.
Oh, Abu Dhabi, great place.
Abu Dhabi,
yeah.
yes.
Oh,
yes.
hi, George.
Hi,
but the world is very little now. Hi. Nice to see you again.
Nice seeing you. Wonderful talk, Enrique. Thank you so much. Enrique, one natural question that appears to me that would be very relevant, and perhaps you could mention a few things, is what happens or how would you expect the theory to change when the diffusivity changes, the diffusion coefficient changes? Because in practical applications, you expect a lot of variation from one region to another. Do you think that perhaps this theory can be extended in these situations? Do you have some insights?
So this is actually what was done in this article with Idris and Domenech Reed, right? So once you see this model with drift, right, you can also rewrite this model with drift as you do in inverse problems, in the classical problem, where you have to identify the diffusivity and you start reducing the problem of diffusivity identification to potential identification, right? So in this case, you can do that. And you are totally right. right? So as soon as the diffusivity is inhomogeneous, right? L large or small depends very much on this heterogeneity, right? This is actually somehow in our drawing here. This is what we already, I didn't have time to go into this, but when I did this drawing, it was already there, right? So when you go to multi-D, what we do is we fix the domain, right? Rather than regulating the size of the domain, we fix the domain, and then by scaling, you know, you get an intensification parameter in front of the nonlinearity or diffusivity. And then you see how, for instance, the fact that all solutions go to zero, of course, this is true for large diffusivity, but which is compatible with, say, small domains. But weak diffusivity, you can have non-trivial dynamics. So, of course, we are in the heterogeneous case. What does it mean, weak or strong diffusivity, right?
Yes.
And this is something that in this way, you can more or less address. But of course, making an if and only if theory for this will be very tricky. And then, yeah, I mean, when you mention other diffusivities, we could have considered, I don't know, P Laplacian, the infinite Laplacian, the porous media Laplacian, non-local Laplacians, and all this is very laborious, right? So what I will expect, George, is that the ideas remain, but that the technicalities in each case have to be worked out very carefully. Unfortunately, this is quite fine, say, technology that you know, relies on some very fundamental pillars like steady states, controllability, stability properties, but working it out requires a very specific treatment of each case, right? Yeah.
Excellent. Thank you so much.
Well, Adris has a question. Adris, it's your turn, please. You have to open your speaker. I mean, open your speakerphone on the left corner, left lower corner.
Yeah. So, thank you, Enrique, for a beautiful talk, really.
Thank you, Idris.
I have maybe two questions. One probably is trivial. If you go to page 21 in your slides.
Yeah.
Okay. So in this control case, which is you gave the example of the penta, basically you control the boundary, Dirichlet boundary condition. However, in case of other applications, like in the epidemics, etc., countries close their doors, and therefore they control the flux, namely the Neumann boundary condition.
Right.
First question, is there similar results concerning Neumann boundary condition control? And
this is a very interesting question, Idris. Yeah, thank you.
Second question, so I will let you answer both of them at the same time. Of course, one can do, as you pointed already out, in the one-dimensional case, one can really understand things very beautifully for these systems because we have better understanding of the steady-state solutions and so on and so forth. What happens when you are in multi-dimensions and the boundary condition will not be a function of time, but will be function in space and time? Is there any progress in that direction?
Yeah. So, I mean, the first question is very interesting. Of course, in this case, because of the maximum principle, I mean, once you solve the Dirichlet problem, you can also read off the corresponding Neumann fluxes and vice versa, right? So the same results, saying it in a different manner, the same results apply also in the case of Neumann control, right? So the trivial way of seeing this, of course, this can be elaborated further, but the basic idea is that once you are able to find these trajectories for control, then by taking the normal derivative of these trajectories, you will know how you have to control the system also through Neumann, right? So this is the first comment. This, of course, apply when you are controlling everywhere on the boundary. Things get much trickier when you say I only control on one piece of the boundary, because then maybe you are imposing the flux to be zero on one side and not on the other, right? So here I am assuming that you can regulate the flux all over the boundary. So this is the first comment, and you are totally right. From a more biological or sociological perspective, maybe flux Neumann control will be more natural, but the result should be the same, is the same, and I should have said that. And the second comment is very interesting. Of course, in multi-D, there will be plenty to be said, right? So here, what I have shown is that you can reproduce the arguments in the radially symmetric case. So then, in the domain omega, you can describe the behavior of steady state solutions, right? Which are radially symmetric. And because of that, you are already allowed to do plenty of things. But as you are saying, Idris, you are not enjoying of the full strength of the problem, because when you are dealing with steady state solutions, which are radially symmetric, basically the control is constant on the boundary. And then you are not enjoying of the added effect that you can have by making the control oscillate on the boundary. This is certainly very tricky. But as I said before, this is really, I think, a challenge even for, you know, the community on elliptic PDEs that will be, okay, can you please revise the classical elliptic PDE theory, Laplace u equal f of u with u equals 0 on the boundary, by now taking u equal to something non-zero on the boundary, and then describe this infinite dimensional bifurcation diagram in which you try to understand how steady state solutions evolve when the boundary conditions start changing. This is a phenomenal work, but it's, you are totally right. This should be done, right?
Thank you very much. Wonderful talk. Thanks.
Thank you, Idris. Thank you.
Thanks, Shi, also for the organizing that.
Well, thank you for coming. And someone named Vodka Kalantarov.
Yes.
You have...
Yes. First of all, I would like to thank you for organization of this very nice seminar, and of course, thank you, Enrique, for a very nice talk. My comment is about the result of Matano. The problem is that, as far as I know, the result about convergence of solutions of initial boundary value problem for reaction-diffusion equations to stationary state to one of the stationary state was established much earlier in 1968 or 67 by Zelenyak. It is published in differential equations, Russian differential equations. So thank you again for your talk.
No, you are totally right. So you see, Varga, the first time I went to Laboratoire Jean-Louis Lyons, it was maybe, I think in 83 or so. I met a lady in the corridor, right? And she was watching the, you know, the list of seminars, and then I was a bit lost. I was looking for probably the secretary of the laboratory, and then I started to talk to this lady in French, and then the communication was not very efficient. Well, I was a bit frustrated. I left. And then after some time, I asked, who was this person? And they told me, it's Olga Oleinik. So,
I see.
So you see, of course, there was a lot ongoing in the former Soviet Union, in PDEs, nonlinear PDEs, homogenization theory, and we are not always well aware of this. So I will really appreciate if you send me this reference, because we keep missing some of these pioneering works, and it's not because we don't want to quote, but it's simply because, you know, we are ignorant.
Okay. Even he did that one for multidimensional case, of course, with conditions on nonlinearity, including the Trotsky-Piskunov nonlinearity.
That's right.
Okay,
Enrique,
thank you again.
Thanks, Varga.
Enrique,
Varga
did not say Olenik, it's Zelenik. It's somebody, it's a man.
No, I understood, but it was just a joke to say that by the time we started to, you know, to work in this business, there was already a lot done, right? We are not always aware of, right? This always also, I try to teach when I teach PDEs to my students, I tell them, you should look to, you know, you should look to the classical works as well, like D'Alembert and Tikhonov and blah, 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 because there were PDEs before Sobolev spaces were invented, right?
Exactly.
Any other questions?
But this will happen with Zoom, right? In a few months, people will think that scientific seminars started with Zoom, right?
Yeah.
And then we will have to say, no, it's not true. You know, there was already an International Union of Mathematics conference by Hilbert over, 120 years ago, right? And people were already communicated before Zoom.
All right.
But I think this battle is lost. For our kids, you know, seminars will be something that is run on Zoom.
All right. This is someone named Lucen Manier. You have a question?
Hello, everybody. Thank you very much, Enrique, for this nice talk. If there is, I want to ask if there is any result about additive control. That means if you have a control on a small region, not on the boundary, but in internal region on omega, for example.
Right. So this is a very interesting question as well. Of course, in 1D, you can do that basically, right? Because additive control in the interior is like splitting in the domain into left and right. And indeed, so everything I said about abstractions and control can be adapted to that case, but it's true that we didn't write it. So this will require some kind of, you know, careful, say, writing of the results, right? But basically the idea is that, yes, everything I said can be adapted to additive control in an internal domain, because then you look to left and right, right? And that's it. In the multidimensional case, of course, this will be related to the questions by Idris and so on. That will be much trickier, right? Because additive control, if you don't make it radially symmetric, then you cannot enjoy any more of the radially symmetric solutions I have exhibited. In multi-D, this will be a much huger step, right? But in 1D, this will work, yeah.
Okay, any other questions?
This should be done also by Carlo estimates, or?
Of course, I mean, the methodology will be the same, right? The methodology will be, in the end, maybe I was not very clear about this, in the end, with these asymptotic results, or these results in which you follow breaches of a steady state, you approximate the target. But in order to finally reach the target exactly, you need to apply a local controllability result. And then you need indeed the Kalman inequalities, right? Otherwise, you will simply get kind of asymptotic approximation results, getting close to the target, but not really to it, right?
Okay, thank you very much.
Thank you, Lassem.
I don't see any first question. Maybe we can join here. Well, for those who are friends of Enrique or friend of me, who I haven't met for a long time, you are welcome to stay for a few more minutes, just have a chat. I mean, I see someone from Brazil, which is a sweet surprise. Maybe people from other areas that I haven't met for a long time. All right, for the rest.
Lassen was in Marrakesh, right? Varga, where you are in Istanbul.
Oh, really? Okay.
Yeah, and Idris is in Cambridge, George is in Abu Dhabi, so we have all the world, right?
Yes. Can you stop sharing the screen so we can watch the video of other people? Can you stop sharing the screen?
Yeah, sorry.
No problem.
Yes, thank you so much for organizing this, Shijen. It's fantastic.
We have been doing it for more than 2 months, so we have had a lot of nice talks and more good talks in the coming. So you're welcome to join anytime.
Yes, I'll definitely join next time. Yes.
We have arranged the best Applied Math talk series in the last 2 months in the whole world.
Yeah.